Welcome to The Explainer. Today, we're going to talk about power, but maybe not the kind you're thinking of. We're diving into the smallest, most efficient engines in the known universe. And the amazing part? They're alive.
All right, let's start with a number. 400 miles per hour. I mean, that's fast, right? That's the cruising speed of a passenger jet. You think of immense power, a lot of noise, and some pretty complex machinery to make that happen.
But what if I told you that number, that 400 miles per hour, is the scaled-up equivalent speed of a single sperm cell? Yeah, you heard that right. If you could take that cell, make it our size, and put it in the air instead of, liquid, that's how fast it would be zipping along. Okay, so this isn't really about just pure speed. The really fascinating part is how. How does a tiny living cell generate so much power, relatively speaking, without a single piston, without any explosions, not even a puff of exhaust? It is an absolute masterclass in efficiency.
All right, so let's get into it. The secret to all this power, well, it's not in the main body of the cell. It's all in the tail, a pretty remarkable structure that we call the flagellum.
You can think of the flagellum as nature's version of a propeller. But honestly, its inner workings are way more elegant. It doesn't just spin around. No, it generates this perfect traveling sine wave that pushes the cell forward. It's beautiful, really.
So if we look inside that flagellum, what do we find? Well, we find this incredible scaffolding. These are called microtubules. They're basically rigid protein tubes. And you can think of them as the tracks that the real engine runs on. They provide the structure, but they're not providing the force.
And this is where you see the true genius of biology at work. This isn't just some random jumble of tubes thrown together. No way. It's a precisely engineered pattern, 9+2. This exact structure has been perfected and kept the same over literally eons of evolution. Why? Because it's the absolute ideal foundation for this kind of movement.
Okay, so who's the hero of our story? It's this little guy, the Dynon motor. These are the microscopic rotary engines that are actually lining those microtubules we just talked about. They are the source of the power. They're the tiny little actuators that make the entire system go.
And, every engine needs fuel, right? For the Dynon motor, that fuel is a molecule called ATP. And here's how it works. Every single time a Dynon motor spends one ATP molecule, it does this tiny little rotation, a single power stroke. Now imagine billions of these doing that all at once, in perfect unison. That's what creates that powerful wave-like motion.
So what we've got here is this silent, incredibly efficient biological motor. Let's take a step back and see how its whole philosophy of making power stacks up against the engines that we humans build. And the difference is, well, it's night and day. Our engines are all about brute force, right? We make controlled explosions to push pistons. And what do we get? A ton of heat, waste, and a whole lot of noise. Biology, on the other hand, it uses a silent, direct conversion of chemical energy straight into motion. It's just elegant. It's super efficient, and it all happens at room temperature. Okay, so we know it's efficient, that's a given, but just how powerful are these tiny little engines? What happens if we try to take their performance, from the nanoscale and translate it into our world, the world of horsepower? So the torque, the twisting force, of a single Dynon motor is this just unimaginably small number. 1 × 10 to the power of -19 Newton meters. I mean, that seems completely trivial, right? But you have to remember, at the scale of a single molecule, that is literally the push of life itself.
But now, look at this number. If you wanted to generate just 1 horsepower, about what a strong horse can do, you would need 60 quintillion of these tiny motors, all of them working together in perfect, coordinated unison. The sheer scale of that is it's staggering.
But here's where things get really mind-bending. Because of the way the physics of scaling works, power doesn't just increase in a straight line. As a motor gets bigger, its volume, and with it, its potential power, grows way faster than its surface area. It's a geometric law of scaling. And what that means is, making these motors bigger doesn't just make them a little more powerful, it makes them exponentially more powerful. So, what happens when we actually apply that law? Let's say, theoretically, we could build a single Dynon motor and just enlarge it 1,000,000 times. Any guesses on the output? It would produce over 13,000 horsepower. That is more power than a top-fuel dragster, all generated from one single scaled-up biological motor. Wild. Okay, let's bring that back down to Earth for a second, to something a little more familiar.
That same scaling law means we could hypothetically build a silent rotor about the size of a basketball with the power of a modern V6 car engine, and it would be fueled not by explosions of gasoline, but by direct chemistry.
So here's the crucial point. This isn't just some fun little thought experiment. This is a blueprint. It's a blueprint for a completely new kind of technology, one that could make us rethink how motion even works.
I mean, just imagine a world where propulsion isn't about brute force anymore. Imagine airplanes with skins that ripple like muscle, ships with hulls that can flex like a whale's, cars that move by contracting their surfaces, all of it. Propulsion without a single piston, without any noise, without any explosions. It's like the ultimate merger of machinery and life.
And believe it or not, this future is already taking its very first steps. Scientists right now are learning how to imitate this motion using advanced materials. They're integrating actual living cells into tiny little robots. They're innovating toward that ultimate goal, a large-scale propulsion system that's built on nature's own design.
So, in the end, that tiny little engine that powers a single cell on its journey, it teaches us a really profound lesson. It shows us that true power doesn't have to come from brute force. It can come from coherence, from efficiency, and from elegance. And it really leaves you wondering, doesn't it? Just how far can these principles take us once we finally learn how to build with that same kind of grace?